Okay, now the limit, we do the Lhopital one time because we know that this is getting 1 minus 1 is 0. This is getting less than 1, it's 0. So it's 0 over 0. We do Lhopital, and we see that it's changed the equations. And when you check again, okay, so always check whenever you do the Lhopital. Okay, so check, and you can evaluate, and becomes the results becomes 4. Okay, I think you did a good job here. Most of you could get a correct answer. The second question here, I think a lot of you also did a good job, but I see some of you got a 0 answer here. The result is 0. So let's see what is this about. Okay, and uh, what can you do to avoid mistake? Okay, so every time you have, this is called the indeterminate powers. Whenever you have this, okay, when you see the infinity over cos pi over 2 is 0. Okay. So this is indeterminate power. And to solve indeterminate powers, so whenever you have 0, 0, and 1, infinity, okay, whenever you have these three type of indeterminate powers, the first thing you need to recognize is you need to involving the ln, or you need to rewrite the form and make it into E ln. This is your form. Okay. For example, this is tangent x cosine x. Okay. Always change to this E form. If you want to calculate the ln first, then you can assume, for example, let y equal the tangent with the power of cosine. Okay. And make ln, and then take the limit. Okay. Take the limit both sides. Okay. For ln and the cosine. So you can bring back the cosine to the front here, right? Okay, because of the ln. So you have the cosine here, and it became cosine ln tangent x. And if you check the form, so always check the form. Okay, so it's 0 infinity. And of course, if you remember, for 0 infinity case, one obvious method is to make the reciprocal, or to make a fraction. That is, we need to force this equation to be infinite, or 0, 0. Okay, we need to force them to make this form. So this is ln tangent x and 1 over cos x. And remember also, if you have ln here, actually, if you have these two different elements, right? But what I do suggest for you is always makes the ln at the top. Okay. Actually, you can do at the bottom, but the result will be very complicated, and there will be a complex process inside, and then it will be very difficult for you to derive. Okay. So it's better to have ln on these top equations. Okay. And then check it's infinite over infinite. Do the Lhopital. Okay. Then you have 1 over tangent x, and then secant squared x. Okay. So let me maybe, before this is cancelled out, let me just write this is secant squared. And 1 over cos, or you can rewrite this as a secant. Secant x is, if you have the first derivative of secant, let me write here. This is secant x tangent x, right? So precisely we have that on the bottom equation. And then we can cancel the secant x with the secant squared. So you have secant x over tangent x over tangent x. Or you can have, or you can rewrite this if you want. Okay, secant x over tangent squared x. Okay. And you can do like what I'm doing here is I try to cancel out this cosine because it's 1 over tangent, it's cosine over sine. I try to cancel this cosine, and I try to cancel the sine, this sine with the bottom one here from the tangent, and it will be this is 1, and this is 1 over cos, so I will put to the top, and it will be cosine x, right? Okay, so the result I get is a limit as x approaching pi over 2 from the left of cosine x, okay? And as you know, and you can also substitute the pi over 2, it becomes 0, okay? But it's not the final result, okay? So remember, the 0 here, whenever you finish the limit, it's not the final result. So every indeterminate powers, you need to rewrite back to the original question. So the original question is this one, right? And this is actually, if you are looking at the 0, this is actually the lny, right? This is the lny. So you need to be convert the 0 back to only 1, right? So we need to raise 0 power to e, right? So we need to have e with the power of 0 that is equal to 1. So that will be the answer. Okay. Okay. Okay, next question is about the this is called the indeterminate difference. Okay. Okay. And the first thing you can do is you can conjugate limit. Okay. Conjugate the limit, and then check the limit when you have conjugated like this. You check it's 0 over 0, right? And because of 0 over 0, we can take the Lhopital rule. Okay. Take the Lhopital rule, and if you see it's still 0 over 0, take one more time Lhopital rule. Okay. And become 1 over x, 1 over x, and this will be 1 over x squared. Then this is precisely take 1 inside. This is 1 over 1 plus 1. It's 1 over 2. Okay. Sometimes if it is in the fractions like this is I believe not really a complicated problem. But sometimes, like we have explained before, that sometimes it's just like e and then x, and then it's actually going to be indeterminate difference. What you can do is first, if you can factorize some variables, factorize x or factorize e, if there is an e problem, then you can do that and see what will be the results. Okay. But if there is a fraction like this, I think it's quite obvious, and you can conjugate the fractions and see the results directly using the Lhopital rule. Okay. I think there are several I think questions in the textbook that is interesting for you, and maybe you can also try, and I can also maybe attach later on. Okay. Maybe tonight I will attach some related questions, mostly about chapter 4 review. Okay. And also I will prepare another additional video for the midterm review. Okay. For midterm review. Okay, any questions before we continue? So this is about the Lhopital and indeterminate forms. Okay. So today's course, I will give you more example on um, optimization because that is our subject last week, and maybe 2 or 3 example. I hope it's enough, and maybe after that we can have more discussion. The next section after the optimization, which is the Newton's method and antiderivatives. Okay, but that's 2 sections. The last 2 sections is quite short, quite short. Okay, now let's start to. Oh yeah, I have given you this, prepare you this question. So I think I can give you a couple minutes or maybe 4 or 5 minutes to think and then to try how to find the closest point on the curve square root of x, and then we need to find the closest point to the point 30. Okay, 30. The first thing you can do is you can try to at least roughly sketch the graph, and I think it's not really complex graph. Okay, if you calculate and maybe find the value, maybe you can state the value, maybe the x value. What is the x value? Of course, the y value will be the square root of that x, right? So first is after you maybe sketch the diagram, um, you can find maybe which suitable um, models or formula to get the optimized function. Okay, anyone fine? Okay, first is if the question is asking the shortest or longest, uh, it means it will have a distance, right? So you can use that distance formula, I think. Okay. You will have a different in y, different in x, right? Using the triangle Pythagorean distance formula. And you can use that formula and then find the first derivative to look for the minimum value. And I believe it will be the minimum value. And you can check also check the second derivative if you want, the concavity. Okay, how about you, Rion? Got it? Okay, okay, okay. Yeah. Okay, good. Okay. So maybe the online students, if you have the answer, you can write the in the chat box if you have calculate. So first, okay, let's see the how we deal with this question. So first, almost it should be 4/2 for the x, and the y is the square root of that. Okay. So first, let me. Okay. Okay, wait a moment for online students because I need to connect this with the. Oh, okay. Okay, yeah. Okay. Now, if we look here, this is 1, 1. Well, for you, you can draw like a roughly sketch if you want, but I think you don't really need to draw, I think, because you can imagine that the point on this curve will be x and square root of x, right? And you have the 0.30, and you can use this, the delta, maybe d is the delta x squared plus delta y squared, right? And then use this as your formula. Okay? But if you still confused, maybe you can draw first. Draw first, I think. Okay. Sometimes you can directly get the formula if you want, but maybe better to draw. Okay, better to draw. Okay, maybe this will be the. It's not too smooth, but yeah. Let's say this is our square root of x. Okay. And then when it's 30 is here. Okay, 30 here. And if you look here, I think this will be the shortest distance. Maybe, yeah, maybe. Let's say this is our x squared of x. Okay, and then we can use the formula. Okay, so the or any variables you take for the distance is this will be x minus 3 squared plus. Okay, and probably, okay, if you get this kind of formula uh, to get into your optimization function or how to optimize functions, maybe the square root here is trouble, right? So we can have another model. Okay, let's say we square this d. Okay, let's make that as our models. I think that will be a better choice, okay, because it will be easier to understand, and because our distance, because it's a square root, our distance should be a positive distance, right? So it should be in absolute value. So we can take the positive value from the square root. So this distance should be in a positive, right? So we can let um, maybe s, or yeah, maybe s is our d squared. So we can have x minus 3 squared plus x. Okay. And then uh, we can take the derivative. Okay, so take the derivative of this s. Okay, with respect to x. So we derive. So this will be 2x minus 3 plus 1. And this should be equal 0. So we have 2x minus 6 minus 5 is equal 5. So x will be 5 over 2, right? And y, of course, it will be square root of 5 over 2. Okay? If you want to check the concavity, you can check the concavity. We derive once more, it's 2, right? Which is positive. So concavity is positive. What happened with concavity positive? It's the concavity will be concave upward, or it will be like this, and precisely it will have the minimum value here. Or if you want to look at the 5 over 2, we can also look at 5 over 2 in a line number, and we can test uh, the signs. Okay, when you have 1 and maybe you have 3. Okay, so 2x minus 5. Okay, if you have 1, it will be a negative, so it will be decrease here, and then it will be increase here. So decreasing and increasing, of course, it will have a minimum value. Okay, so it will be the closest distance between 3, 0 to the curve square root of x. So maybe it's not really a straight line. Maybe this will be around this and this. Maybe this. The point that we have calculated. Okay, any questions? Any questions? I think still not really complicated, I believe. Oh, by the way, last week I think we still have one questions, right? Or we have already done. Oh, this one. Okay, this one. Okay, maybe I will copy this and start to work on this problem. I forgot to finish that last week. So let me go straight here and put here. Okay. Okay, so we have hyperbola xy equal 8, or we can make it 8 over x. Okay. And we need to find the closest. It's also the same question. I'll find the closest to the point 3, 0. Let me check the. Okay, if we have the x-axis, y-axis like that. Let me make the y equal 8 over x. So this will be 1. Okay. Okay, let's say that is our hyperbola. And I have the point is 3, 0 is here. So we need to find a point in the hyperbola that is closest to maybe this line here. And I think I draw really proportional. And I think this is similar to the answer, I think, 4.42. But let's check. Okay, let's check whether it's correct or no. Okay. So we have the x and 8 over x. This will be the point, okay, the point here. Let me erase this first. Okay. Let's say we have x and 8 over x. And we have 3, 0 here. So we can use the distance formula. Distance formula, x minus 3 squared plus 8 over x squared. Okay. Maybe if you confuse with x, okay, maybe you can take this with a or an 8 over a. If you confuse with the variable x in the x-axis, you can do that also, but I will just use x, okay? And similar with the previous example, we can let this with some s and take the s as a d squared, and we can have x minus 3 squared plus 8 over x squared. And we can take the derivative directly, I think, to take the first derivative of f, the s prime. We have 2 x minus 3, and then this will become minus, right? Minus. This is from this 64 x squared, and this will become 128 and x cubed, right? And take this equal 0. So we will have 2x minus 6 minus x cubed equals 0. Okay, let's solve a little bit. Solve this. It will be 2x4 minus 6x cubed minus 128 equals 0. I think we can divide all by 2. Okay, and the way we can solve this is take the factor 64, okay, and this is factor 1, right? So we can just focus on this factor 64, what kind of solution we can have. 1, 64, 2, 32, 4, 16, and 8, right? So we can have 7 kind of numbers that we can take. And let's say this is our function of x here. From positive value here, it changed only one time. So we can take only, there will be, definitely there will be one positive root. Okay? So from 164 to 32, 4, 16, 8, we can try the positive number. Okay, we can try the positive number. Actually, this method is, you can try, just try the number and see if it is 0 or not. Okay, that's one way. Okay, but I want just to narrow the answer. Like maybe we try from +1, +2, positive +1, +2, +4. Okay, we can try these three numbers first. Okay, and also if you want to try the negative part of the functions, we can take this in terms of the negative. This becomes a positive, and this will become negative, negatives plus. This become a negative, so we will have still one one sign change. It will be precisely having one negative. But let's say we try the positive one first, because we don't really need the negative, right? Because the answer cannot be a negative, right? Okay, it's a logic reason, right? So we can just ignore this part here. The There will be no negative root, right? So the positive root, we can take this 1, -3, 0, 0, and -64. Okay, if we take this, take the polynomial division, syntactic division, take 1. This is going down here, multiply. I hope you still remember this method. And then we get, I don't think we will get the result here, right? So let's change to another number. Change to 2. I think we still doesn't get any 0, so let's skip this, ignore that. And doing 4, I think we will get 4, the answer. Okay, so x equal 4 will be our positive root. Okay, and we only consider the positive root, right? So the x that possible for here after trial and error is x equal 4. So this x equal 4 is our critical point. We can check the line number 4 so that this is correct. The first derivative is x with the power of 4. Okay. If we check 1, it will be a negative, right? If we check 5, of course, it will be a positive, right? So it will be decreasing, increasing, and of course, this will be a mean value. Or we can check this is s prime, the double prime, or the second derivative. This will result, but of course, you need to have some solution from here as well. So there will be, I think, an inflection point. I think. So you need to check this 9 over 4 to check the concavity. But I think you don't need to check that part. You can just check this, and we can really know that this will be the minimum point. So our solution here is 4 and 2. Okay. And I think what Efando doing is this problem, I think, for 2. Yeah. Okay. Okay. But the idea is similar, okay, from the previous one. Okay, the first question I gave you, uh, the distance formula, it has the square root. You can take the squares to remove the square root. You can make another model that is suitable. Okay. Okay. Any questions? Any questions from here? Any questions? Okay. Okay. Well, the part here, okay. Actually, this part here to solve the x with the power of 4 is actually additional. Okay. So if you think you can just do trial and error, you can do that. Okay. I think because this x4 and x cube, I think to calculate it's not really a big problem, right? If you maybe forget what is this about, and you can just try maybe 1, 2, 3, 4, I think you will get the answer. Okay. But this is just to let you know that if you have this kind of polynomial, you can check the factor here and factor here. Usually the roots will be the factor of this divided by the factor of this, the constant. And you can check the possibility, okay? So that you can check those numbers. Okay? You can check those numbers. And if you want to check the signs, you can check the change in the signs. Okay? If this is changing positive, negative is one change, right? So if there's only one change, there will be at least one positive root. Okay. If it has two chains, it will be having two positive root or zero. There will be no positive root. But that is just prediction. Your prediction from the sign. If it is you take the negative x and then put inside this x and do the same thing, you can take uh, see the change of sign. If it is 1, then it will be 1 negative root. If it is 2, it will be 2 negative root or 0. If it is 3, it will be 3 negative root or 1 negative root. Okay. But I think that will be the maximum for uh, questions in our calculus class. It can be actually long because it's polynomial. It can be as high as possible, the degree. Okay. The degree, this is 4. But I think for calculus, we can just stick with around 4, 3, 2. Okay. Higher than that, I think to solve with the factors, to find the factors, I think it's not really often. Okay. Okay, I think we can just go to the next part. Okay. Okay, I will just give you the next question here. So a typical problem in an optimization is finding the distance like we have done before. Find the shortest distance, the closest, um, the volume, okay? Either surface area and you have the volume, or you have volume and you want to find the surface area. It can be those kind of problem. It can be a cone, maybe a cube, a cylinder, okay? And you need to remember some formula, basic formula, okay, for geometry. What the volume of cone, okay? You need to remember, okay? Remember that. And also the other typical in optimization is, I think there are several questions that is similar to related rates, okay? Like someone moves and the other also moves, and you need to find the optimum, maybe the optimum distance, maybe the optimum velocity, that is also possible. But let's try this one. Okay, if I may, right? Okay. This means that the R will be here, right? And let's say we have a small r as the base, the circle, and the height will be this one. Okay. So maximum capacity means finding the volume. Okay. Let me give you a few minutes for solving this one. And if you don't remember the volume, okay. Another thing important for you, uh, you see the volume here, okay? It's 1/3 pi, and you have r and h, right? We only have a constant, this the big R, right? So we have two, we can say two variables that might change, right? The key in optimization, we need to make it into one variable. Okay? It either can be h or r. Okay, okay, got the idea? Okay. So you need to make one variable. How to make one variable? You need to let uh, the information, okay, from the question. If you see the questions that is having a constant r, that is actually your constraint. Your constraint. Okay. So the big R here is your constant, right? So this small r and h is dependent on the big R, right? So you can take relations from the small r with h with the help of this r. Okay. Okay, let me give you a few minutes to try. Okay. Okay. And because it's only specified, you need to just find the volume. I believe there is some a suggestion for you. Okay? If you see what I'm doing here, okay, this constraint will be R H, this big R like that, right? If we see the equations between the volume and this relation of the triangle RH to big R, you see all is squares, right? My suggestion is to help you simplify the solution. You see this also square, right? Okay, let's switch this with this. Okay. So if you deal with that, we only have and use this to switch with this. Okay. So we have volume. Okay, or we can break out this equations become this. And now we have the big R is just a constant, and we only have H. So we can take derivative. Okay, rather than if you, okay, for example, from here, you want to just, or you want to have the H. The H is having a square root something, blah, blah, blah. It's doable. You can do it, but it will be take a longer time, right? Rather than just using this, you can definitely see, okay, I can derive 3h squared, right? So we can derive this. Okay, and then we can just say, okay, it equals 0. We can find the h. Okay, we can find the h. And we can find the h is I think I need to make this pi. Oh, wait. I need to make this pi over 3. Pi over 3. Let me correct this mistake. Okay. So this will be, or maybe pi over 3 r squared minus 3 squared. I think that will be better. So r squared is 3a squared, or a squared is 1 over 3 r squared, which is 1 over square root of 3. Yeah, I think that will be better. Okay. And then because we have this h, then we can take this h into our solution. So volume is this will be 2 over 3 r squared at 2 over 9 pi 2 over 9 square root of 3 r cubed. This will be the volume. But if you want to check also the line number here, like the 1 over square root of 3 r from 0 to r, right? I think this will be resulting the maximum. Or you can check if the concavity. This will resulting negative 6h, right? Negative something 6h 3 pi. So it is negative, so this will be less 0. So you will have concave downwards, right? Okay. Have you checked the questions that I attached? I think I attached some uh, optimizations problem. Have you checked that part? Uh, if you have difficulty on some numbers, okay, you can let me know which part, okay, and I will consider to make some additional video for you, okay, so for having some solution for you, because I don't think we can have much time to solve in class, and also I also give your TA some suggestions for some questions, and because I also in the middle of progress for your what kind of questions for you. Okay, I already have some, and I still edited the question. Okay. Okay. So far, is there any anything you maybe feel difficulty, or maybe you check the question from textbook, and maybe you want to confirm, or maybe still confused about something? And by the way, this kind of question is a typical question. So maybe your midterm will be a little bit higher than this one. So um, you need to prepare yourself. Okay. Okay. From the online students, do you have any questions? Why do have we find? Oh no, the second derivative is just to show you that it is concave downward, so that our solution is the maximum value. Okay. This is like I told you last week, I think. Uh, the questions, for example, here, find the maximum capacity. Okay. If the questions change to find the minimum capacity, it will be really troublesome, right? And because the textbook, I think most of the questions is already asking the right questions. It's asking maximum, and it is of course the critical point, the maximum one. And if it's asking the minimum, so that the critical point is most of the case is uh, the right question. Okay. But sometimes maybe I ask in the midterm with different questions that also can be a problem, right? So you need to understand how to justify that this answer is correct. So we are not only looking at the okay, we get h is this, volume is this, okay, that's our answer. No, no, no. That is just calculations, just our process, right? What's important behind this is we understand that through this, okay, through this calculus part here, we find out that we have a critical point here, and that critical point is our local max value. With this critical point, it will be a local max. So that is the calculus part. The other part here, the geometry, blah blah blah, is that is just an additional part. Okay, in calculus, if we think with calculus perspective, it will always be the derivative. Okay, within this part is the derivative. Okay. Remember, calculus is just two parts: derivative and integrations. Just that. The rest of it is just additional to help solve the problem within the derivative or in the integration. Okay. Okay. Next question is actually this is uh, the I think other questions. It's it's similar but with some additional information. But I think you can try first, and but I think I don't have time to uh, work on that today. So just take some notes, okay? Let me check if I have time. I don't think I have time for this question. Okay, let me give you some clue, okay, on what is this question about. We can try to draw first. Draw the 3 over x. I'll just roughly draw. Let's say this is y equal 3 over x. Okay. So what is the question? Is the question is saying that there will be a length, okay, of the line segment. So there will be a line, okay, and it's cut off by the first quadrant. So first quadrant is this part here. This first quadrant is here, the positive one, x positive and y positive. That the first quadrant. So the line is cut off by the first quadrant and it's the tangent to the curve. So you can take any point here and then make that, and it's cut off the first quadrant, right? Okay. So that will be the the schematic diagram. And let's say that that's our line. Okay. So we need to find this line from here to here. Okay. Let's name L. That's what we are going to find. And we need also to find, and maybe just make it some point A and 3 over A. That one. Okay. So I think I can give you this for you to try. Okay. The key is to use the line equation, slope equations, okay, and try to find uh, the distance, okay, distance L. This will be having a formula. So this will be a constraint. This will be your optimization. And I think you can get the answer. Okay. I will give that to you. Okay. And we move to another part now. Some additional parts. If I have time, I will go back to this question. Okay, but now let's move to the next section. Okay. This will be about the 4.8, but this is just an additional notes for you. This is called the Newton's method. I hope you still remember. Okay, I have given some brief intro for Newton's method before. Okay, remember that you have the line equations. That is this. This is the formula, right? And you can rewrite this becomes this, right? Okay. If you remember the mean value theorem, it's also similar, right? It's similar. And also the linear approximations, also similar linear approximation. If you remember that, you will have a similar approach, but the difference is just this approximation symbol. This is F A. Usually we have A here, and then the M is F prime A, the tangent, and this will be X minus A. Okay. If I write this in just a line equations, let's say we have an X, and uh, let's say we have the A is our X0. Okay. The Newton's method, if you remember correctly, if this is f of x, Newton's method, you want to find the roots on the curve. Okay, so you want to find when the functions is 0. You need to find the x. Okay, so the idea behind this is, okay, remember, I don't want you to mainly memorize one by one. Okay? I just want you to remember just line equation, and from that line equation, you can have mean value theorem, you can have linear approximation, and you can have the Newton's method. Okay, but if you think maybe you need to memorize, it's up to you. I don't want you to memorize too much. Okay? But one thing in the Newton's method want to have this equal 0 because you want to find this, right? Like when you have a quadratic, you have two roots, right? So this is actually you want to have this. Yeah, you want to have this. So we take this 0. Okay? We take this 0, and we can switch the formula, and we want to find this, the x, right? Okay. So the x0 is something that is actually, so x0 is our approach or approximation or our numbers that we want to try. This is a constant. Let me write the so we can write this. Okay, and I can make this x. Okay. Now, what does this mean? Okay, what does this mean? Okay, let's say we have this x0. Okay, let's say the x0 is not exactly at this point, because if we have this exact at this point, we already know the answer, right? That is make it the whole function becomes 0. So let's say our x0 is nearby this point. Okay, let's say the x0 will be maybe around here. Maybe too far. Maybe here. Okay, let's say this is our x0. Let me erase this part first. And this x0 have tangent line maybe here. Okay. And let's say we have another point here. say this is x1. Okay. So this is actually x1. Okay. So x1 will become, okay. Now you look here, okay, we have x0 and we got the tangent line. Oh, it's here. So actually we are going to have more tangent line so that we can get closer to this. Okay. This picture is easy to see, right? Because we just draw and then, okay, we know, let's say we know the tangent line over here, here. But if, okay, you only have the function and it's maybe a complicated function, okay, what you can do is actually you can find the first derivative, try the number that you think may be nearby the point that you want to look for, and try several iterations. For example, we try x0, we get the x1 here. Let's try x1. Okay, we try x1. Take this into our approach to the curve and take another tangent line. Okay, now it's getting closer, right? If you take maybe one more, maybe it's will be the accuracy will be better, right? So we take this maybe x2. This is x2. Maybe different color. So this is x2. So actually, we can have as many as we want. And the idea is just using you plug in the x1 to the functions, divide by the first derivative of it, find the value. You have the x1 from previous calculation, try to minus, and that will be your x2. If you think it's still not really close to your answer, try x3, x4, as many as you want. So this is an iteration. So it's just like an algorithm to find how your calculators work. This is how. Maybe you want to find square root of 8 blah 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 3. It's like a linear approximations. This is also similar. They will try an error and find that has small error, right? So the error will be your x and approximations. So your x your x. So this will be your error, okay? And also if you have more and more, okay, this will be your error, okay? The difference, when the difference is becomes so small, then it's better. Okay? It's better because we have approach a correct number that we want to find. Okay, so that's the Newton's method. So Newton's method it's really simple. It's really simple. You can take as many as you want, and then you want to find, like, maybe you have a complicated function. You can just put the functions, take the derivative. Okay, of course, it will be easier if you just type in the functions, and maybe yeah, probably this will be a basis for any computations method, one of the computation method, like a numerical approach, right? If you want to, maybe in the future you want to learn this and maybe relate to maybe if you want to learn like MATLAB or something similar to that software. I think one method to have the numerical approach is this Newton's method. Okay. Okay. But okay. This is good, powerful, but it has a weakness. It has a weakness. And I think it is, I think, obvious weakness. Okay, let's see. Okay. Let's make another page. Make another page. Let me write here Newton's Newton's method. It works very well if the f prime not small and the f double prime not too big, and the point that you approach the x0 should be stars nearby, not too far. And Newton's method can be fail. So, you know, not small, not too big, so that the graph is if the graph that nearby of x0 is almost similar to tangent line, it will be better because it can help the tangent line to approach right easily. But if it's too far, maybe like a curvy too curvy, like the f prime and f double prime is maybe too large, okay, so that the concavity is the curve it's more curvier. Sometimes the Newton's method it's not work very well. Maybe you need like a lot of repetitions to get to the real roots, right? To the roots, okay. And also the fail, okay, can be also happen if like I mentioned it's too far. For example, let's say this is the let's say this is the functions, the curve, and maybe maybe it's here around here, or maybe around, let's say this is around here, or maybe here to take the obvious part, maybe the x0 here. If I take to the curve, the tangent will be too far, okay, too far. So this will be too far. Okay. So we take the wrong x0. Oh, so we need to change our x0, and we need to change the maybe the x0 should be around here or around here. That will be correct because it will be giving us better expected results, right? Okay. This is too far. Okay. Okay, another failure that we can also have if we have let's say we have this. Okay, that is okay. For example, we take x0 from here. Take from here, and maybe this will be the tangent line. Okay, so we get the another x1. Okay, and then you want to take this x1, but then goes back nearby the x0 here. Or even sometimes the failure, maybe it's far away from the x0. And this is not our expected results. Okay. So this is also one problem in Newton's method. So there will be a cycles. So from x0, x1, and then it's back to x0 again. Sometimes it's happened. And of course, in our computations, it is a drawback, right? It is make the computations works too really long. We want to have as fast as soon as possible, right, to get the answer. So again, the idea, you need to expect the x0 to be near as possible. If you think that you cannot imagine the curve, then when you calculate, if you see the answer is like forward, backward, the number seems forward and backward, then you can maybe skip that and then try from another number. Okay, another number. You take the wrong approach. Okay, we take the wrong approach, wrong x0. Okay, so that's the method, Newton's method, and how the Newton's method can be failed. Okay. The next one is 4.9, but I think I will just take some brief intro because it is just the preview your chapter 5, the integral. So I will just make some brief intro. Okay. If we need to take some discussion, we can go back and discuss. But let me go through the antiderivative. Okay. So basically, let me start with this. So calculus. Okay. So first is derivative, right? So your chapter 1 to chapter 4 is about the derivative, right? The second one is about the integral. This will be start from chapter 5 to chapter 8. If we cannot finish chapter 8, that's okay. We can finish just chapter 7. That's still okay. Chapter 8 is short. So for integral, to begin with, integral is basically we take the two approach. Okay, we take intuitive definitions. And geometric. Okay. Our intuitive definition here for integral is based on the antiderivative. We call antiderivative. So we are not officially using the integral terms. We say it's antiderivative. In geometric, you will learn the proof on why you can use the integrations to integrate the functions. And we are using the approach from Riemann sum. Okay. So from this, I think I can give you some words to for the official definitions. So a function, let's say a function with a big capital F is called antiderivative of a function small f, okay, on interval, some interval, okay, some interval I, okay, if okay, the derivative of the big F is equal of f of x for all x on interval. Okay. And also as a consequence, if f, the big F is antiderivative of f on interval I, the most general antiderivative of f on I is plus c, where c is an arbitrary constant. Okay. Oh, maybe another terms that usually we are maybe you remember also. The antiderivative, usually we say this is indefinite integral. The geometric one is the definite integral. We can also make that as well. Okay. Now another theorem, if okay, the big F prime is equal to another functions g prime, then if you take this into one side equals 0, if you take this and find the antiderivative, this will be resulting a constant, okay? So that the f of x equal g of x plus c. So if you have f of x, the small f sine x, okay, then the big F, the integral, if you would like to say that, is negative cos x. Okay. Because if you have cos x and you want to derive, this will be resulting negative sine x. Okay. So how to get this is you need to think how to reverse this, okay? How to make it forward and backward, okay? In integrations, it's not specific official method, but some professor, they will also sometimes they will use this, and it's called the advanced guessing method. Okay, it's not like if you have integral, maybe you remember there will be like substitution, integration by parts, and so on and so forth. Some method, right? This is just a simple way, just advanced guessing method. Like you think what kind of functions or what kind of functions before it was derived, and you simply prove that by reverse the functions, and then you find the derivative, and then you prove that, okay, that's true, and then you find the integration. Okay, so like when you find, you have the sine x, you need to integrate, and you need to take what is the form before the sine. What is the form before? Okay, we if we say cos x, we have to prove that when we derive this, it becomes positive sign. So when we derive positive cos, it's negative. So we need to add a negative here. Okay, so that's the intuitive definition. When we learn integral later, when we learn the method like substitution, integration by parts, that's good. Mostly you can solve many problems with that method. But this, I think this will also can help you in a way that some difficult question you can, especially in integral, you can solve using this advanced guessing method. It seems simple, but it's actually powerful. Okay, I'll show you maybe later when we have deal with the integrals. Okay, since we don't have much time left, okay, I will just stop here. And there are some, I think, from your derivatives, like um, the ln x, you can derive this, right? And it's become 1 over x. So if you have 1 over x, then you can at least making this integration, and this is making it this ln x plus c. Okay, and you have the tangent inverse, right? And you can have this 1 over 1 plus x squared. So whenever you have this 1 over 1 plus x squared, you know that you can reverse it and make it tangent inverse x to take the entire derivative. Okay, so please check the what we have learned on the derivative part, especially the basic one, and take the antiderivative or the integral, and that will be the form for most of antiderivative. Okay. On the midterm, this will be not really much questions about this, and maybe not at all. Okay, because this is just review of derivative actually. Okay, what kind of form before that derivative, right? Okay. Okay. I think we can take some feedbacks. Okay, we can take some feedbacks time. And wait a minute. Let's check. Let me check first. Okay. Let me add some. Things. Let's see. Oh, okay. Okay. I hope you ready. Okay, let's start. Okay, start. Okay, 3, 2, 1. Okay, start now. Oh, wait, wait, wait. Yeah, I think 3 minutes. I think enough. Use fractions, not decimals. Okay, not decimals. So maybe if answer 1/2, you need to write 1/2. Okay. 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 Okay, 1 minute, 50 seconds, 56. Okay. Okay, 5 seconds. Okay. Remember, it should be positive, right? Because it's about distance. The sum getting -9/4. Okay. Okay. Good. Okay, Rion. Very good. Very good. Okay. Next question. Okay. Last question. Okay, let's start. So find the point. So you may write, like, for example, 2 and then 3 with a comma. Okay, with a comma. You need to write with a comma without space. Or if it is a fraction, then 1/2, comma 2/3. Okay, that. Or if you want to use bracket, also fine. But not having bracket, also okay. I already prepared the answer for all conditions. I hope the time is okay. I hope the time is okay. Okay, okay, good. Okay. I think there are several other answers, probably because you are using space. Okay, okay. Sorry, sorry. Okay. Okay, congratulations. Okay. Um, that will be the end of our lecture. Okay. Hopefully, this Thursday I can review uh, chapter 1, 2, 3, 4. Maybe not all, but maybe some that I think necessary. for the especially some questions from maybe last year midterm that is essential and maybe not really discussed yet with your TA. So your TA after this will discuss that part, and hopefully you can take some study for those problems so you can have idea what kind of questions that you might have in next week. And of course it will be different questions, but at least you know the difficulty. Okay? You know the difficulty and how well you need to study. Okay, and please study for the midterm. Okay, uh, not only for the midterm, for the course. Okay, so for the course. Okay, so yeah, thank you everybody. Thank you for joining in, and see you this Thursday.